What if I told you you could look inside the human body without cutting it open? You can't see through skin. You can't see through muscle. You can't see most of your organs with your eyes. And yet, doctors can watch a heart beating, observe blood flowing, and even see a developing baby using something you cannot see, and sometimes cannot even hear: sound. This is ultrasound. But here's the fascinating part. Humans didn't invent the idea behind it. Nature was using it long before we were. Long before ultrasound machines existed, bats were already using high-frequency sound to navigate the darkness. A bat sends out a sound. The sound travels through the air, hits an object, and comes back. The bat doesn't see the object directly. It listens to the echo. From that echo, its brain can determine where something is. And beneath the ocean, dolphins use a similar strategy. A dolphin clicks. The waves hit a fish and return. The dolphin sends sound into the darkness, waits, listens, and interprets the returning signal. Nature had already discovered something incredibly powerful. You don't always need light to detect the invisible. Sometimes, you just need a wave. Ultrasound is simply sound with a frequency higher than humans can normally hear. Human hearing extends roughly up to 20,000 vibrations per second. Ultrasound operates above that range. But don't think of ultrasound as some mysterious, invisible radiation. It's still a mechanical wave. Matter vibrates, and that vibration transfers energy through the material. Imagine pushing a row of tiny particles. One particle moves, pushes the next, which pushes the next, and the disturbance travels forward. The particles don't have to travel all the way from the source to the destination. Instead, the disturbance and its energy propagate through the material. Humans eventually understood the physics behind echoes. And then we asked, what if we could control the sound ourselves? What if we could send sound into the human body and listen to what comes back? This is the ultrasound probe. Inside it are special materials called piezoelectric elements. Electrical energy convert to mechanical vibration, and the mechanical vibration change into ultrasound. Or an electrical pulses change to crystal, to vibrating crystal, to sound waves. When an electrical voltage is applied, these materials deform and vibrate. That vibration produces ultrasound. Sound wave travels into body. Reflection comes back. Probe receives it. But here's something even more amazing. The same material can work in reverse. Returning wave hits crystal, crystal vibrates, electrical signal appears. When an ultrasound echo hits the piezoelectric element, the mechanical vibration is converted back into an electrical signal, like sound to mechanical vibration to electrical signal. So the probe is essentially both, a speaker and a microphone. Now, the ultrasound pulse enters your body, but your body isn't one uniform material. Skin is different from fat. Fat is different from muscle. Muscle is different from blood. Blood is different from an organ. And whenever a sound wave encounters a boundary between different materials, something interesting happens. Part of the wave continues deeper, and part of it is reflected back. That reflected wave is the echo. And this echo contains information. The machine measures something incredibly simple. How long did the echo take to come back? If we know the speed of sound in the tissue, and we know how long the pulse traveled, we can estimate how far away the reflecting boundary is. Distance is equals to speed of sound times time traveled divided by 2. We divide by 2 because the sound traveled the distance twice, there and back. But one echo isn't enough to make an image. The machine sends thousands of pulses, receives thousands of echoes, and processes the returning signals. Stronger echoes produce different brightness. Different arrival times indicate different depths. And together, these signals create a picture of structures hidden inside the body. But ultrasound doesn't just show structure. It can also show movement. The heart contracts, valves open and close, blood moves, tissue moves. And because sound interacts with moving blood cells, ultrasound can also provide information about blood flow. This uses another beautiful idea from physics, the Doppler effect. When something moves relative to a wave, the frequency we detect can change. The machine analyzes that frequency shift and can estimate the direction and speed of blood flow. And now we can see the bigger picture. The ultrasound machine isn't magic. It isn't really seeing through your body. It's doing something much more fundamental. It's asking nature a question with a wave. A bat sends sound and listens to an echo. A dolphin sends sound and listens to an echo.
An ultrasound machine sends sound and listens to an echo. The hardware is different. The biology is different. But underneath, the physics is remarkably similar. Nature doesn't always reveal its secrets through light. Sometimes, it hides them inside vibrations. A bat learned to listen to echoes. A dolphin learned to navigate an invisible ocean of sound. And humans learned to transform the same physics into a machine capable of looking inside the living body. We didn't invent the language of waves. We learned how to listen to it. Because beneath the machine, beneath the biology, beneath the technology, there is something much older: physics. And physics is nature speaking in mathematics. Fight your channel. Physics inside nature.